All right, let's take a look at section 12.3, which will cover the dot product. So, a few learning objectives this time. We'll define the dot product and relate the dot product of two vectors to the angle between them. Do a few computations involving the dot product, and finally, compute and interpret vector projections. But starting with the first part, the angle between two vectors and the dot product. So if we call theta the angle between two vectors A and B, then we end up with the following formula that says that A dot B is equal to the magnitude of A times the magnitude of B times the cosine of the angle between those two vectors, where A dot B is the dot product of A and B. The dot product is defined in the box below, where it says if we have two three-dimensional vectors, then the dot product between those two numbers, or between those two vectors, is a number where we just multiply each of the components together and add them all up. So that means we're going to multiply each of the x components together, then multiply each of the y components together, and then multiply each of the z components together. So just write down the line, multiply line by line, and then add those pieces up. And again, we'll call that the dot product. Some other things to say about the angle that's between these two vectors. If we rearrange the equation given, we can say that cosine of theta is equal to the dot product, so A dot B divided by the magnitudes of those two vectors multiplied together. So if we're looking to quickly solve for the angle that is between two vectors, we should be able to say that theta is the inverse cosine or the arc cosine of the dot product divided by the magnitudes. We'll remember to put hats on each of these because they are all vectors. So to reiterate a point about the dot product is that the dot product will take two vectors and multiply them together to get just a scalar value. So the solution to a dot product is just a number rather than another vector. We also have one more interesting tidbit that we learn about the dot product based on the definition above. And that is because cosine is a number that's always less than or equal to 1, we have that the dot product of two vectors is always less than or equal to the multiplication of their magnitudes. So the dot product of two vectors should always come out to be less than the magnitudes of the two vectors multiplied together, unless those two vectors are parallel, in which case cosine of 0 is just 1, so we end up with the dot product is equal to the product of their magnitudes. But we call this particular inequality the triangle inequality. Right. Let's move on then to a definition of what orthogonal vectors are. So we'll say that two vectors are perpendicular or orthogonal, which is the three-dimensional word for perpendicular, if the angle between them is 90 degrees. So same definition for orthogonal that we have for perpendicular, just again, orthogonal lets us expand into 3 dimensions. And we have a theorem from this section that says that two vectors A and B are orthogonal if and only if the dot product of those two vectors is 0. Since based on the theorem that we had previously, if we take the cosine of 90 degrees, we get 0, which means that the dot product would be equal to a magnitude times the cosine of 90 degrees, which is 0, so all works out to 0. If we take a look over at figure 2, we've got a few different example angles between A and B and what that means for the dot product. So we'll say that the dot product is positive if the angle between them is an acute angle. And then we'll have that if that angle is 90 degrees or pi over 2 radians, the dot product comes out to 0, which means that if the angle is obtuse, the dot product should come out negative. And really, we can just follow the values of cosine to figure out what the dot product will look like based on our angle theta. Acute is positive because cosine is positive in the first quadrant, and the dot product is negative if we have an obtuse angle because cosine is negative in the second quadrant. All right, and then we have a few more properties of the dot product for vectors A, B, and C. And we'll also make a distinction between bold C and regular C, where regular C is a scalar, but if C is bold, that means it's a vector, according to the text. And we end up with a few interesting properties. The most exciting of which is number 2, that says that the dot product of A and B is equal to the dot product of B and A. So we can take the dot product in either order and come up with the same answer. All right, and let's take a look at some examples then with this dot product. So we're going to calculate the dot product between A and B in each of the following cases, and then based on that dot product, determine if those vectors are orthogonal. So starting with A and B, well, I guess they're all A and B, but starting with the first example, I want to take the dot product of those two things. So I'm going to start by multiplying the x values together. So I should have 1 times -1 plus, if I go into then multiply the y components together, I'll have 0 times 3 plus, looks like I should move this just a little bit to the left, multiply those z components together, and I'll have 1 times 1. Let's see if I bring this down a little bit. Bring that back up there. We were saying that A dotted with B is equal to that line below, which in turn is equal to -1 plus 0 plus 1, which comes out to 0. And so we said that as long as the dot product came out to 0, we had a set of orthogonal vectors, because the angle between those two vectors must be 90 degrees, because the cosine of theta must come out to 0. Orthogonal for those two vectors. And again, the dot product comes out to just a number because we take all of the components of our vectors and multiply them together. All right, let's then take a look at the next example. So we'll look at A dot B and see what we come up with. So we'll start with the x components. This time it's written in terms of the basis vectors. And in A, we have 3i, but B is just 2j plus 4k. So there is no I term, meaning that the coefficient on I is 0. So for the x component, we get 3 times 0 for the x component of that vector, or the I component of that dot product. Then we'll add to that the y components, which are -2 and 2. So we've got -2 times 2. And finally, the z components, 1 for A and 4 for B, so 1 times 4. So in the end, this thing comes out to 0 -2, or -4. That's what happens if we multiply 2 and 2 together, plus 4, which once again comes out to 0, which means that again, we have a pair of orthogonal vectors A and B. Then with the third example, things get a bit more interesting because we're going to define A and B as the directed line segments. They go from A to B for vector A and from point C to point B for vector B. So we'll start by just calculating what those pieces are. And also, this will be just a 2-dimensional dot product instead of a 3-dimensional dot product. So we'll get that as well. So if we look at vector A, in order to get that vector, we're going to take B and subtract the point A. So we'll have 5 minus 3 in the x component, and then we'll have 6 minus negative 2 in the y component. So 2, 8 is our vector for A. Then we'll take a look at vector B, which in order to get B, we're going to take the point B and then subtract the point C. So final minus initial. So 5 minus negative 1 and 6 minus negative 3 gives us the vector 6, 9. Nice. And then we'll take the dot product of those two pieces. A dot B should be equal to, we sort of highlight where these pieces are going to come from now, 2 times 6, so the x component, and 8 times 9 for the y component. Which, that'll be 12 plus 72, which if my math is okay, that should come out to 84. Now this time we took the dot product of two vectors and got a number other than 0, which means that these vectors are not orthogonal. But we don't really know, just from looking at the dot product as a number, we don't actually know anything else about them. Or I suppose actually we do kind of, because the dot product came out positive, we know that the angle between them is acute. So whatever angle is between A and B, it's going to be less than 90 degrees. Right. Now let's shift gears and start talking about a projection. So when we talk about vector projections, that means that we're going to have to take two vectors that, for sake of example, are going to point in different directions. Two I'm going to start with are A and B, A drawn in blue, and B being that longer vector drawn in gray. And if I want to look at the projection of A onto B, that means I want to take the component of A that is in the direction of B. So if we look at the diagram that's there, the vector drawn in yellow, that vector C, is going to be the projection of A onto B as we define it. So if we just draw that vector B, construct a perpendicular line or an orthogonal line on B that's going to intersect with the tip of A, then the projection of A onto B is going to be the point from the origin that goes to the intersection of that orthogonal line along B. And so again, the way that we'll want to think about that is that C is the component of A that is in the direction of B. And if we want to call angle theta being the angle between angles A and B, which means it's also the angle between A and C, we end up with a right triangle that contains the vectors A and C, and then a part of that line that's perpendicular to B, which means that if we were interested in calculating the magnitude of our angle of our vector C, we could just use trigonometry to get that. I have the hypotenuse and the adjacent side, which means I'm going to want to use a cosine function, since cosine is equal to adjacent over hypotenuse. So the magnitude of angle C should be equal to the magnitude of vector A times the cosine of theta. And I think I misspoke a moment ago. I wanted to say the magnitude of vector C is equal to the magnitude of A times the cosine of theta. was weird. If we just move that over a little bit, we know something about the cosine of theta, since theta is the angle that's between vectors A and B, so that cosine of theta should be the dot product of A and B divided by the magnitude of A times the magnitude of B. Which means that if we just replace that for cosine of theta, I'm going to have a magnitude of A in the numerator that should reduce to the magnitude of A in the denominator, leaving us with just the dot product of A and B in the numerator. Again, this coming from our definition of the dot product, divided by the magnitude of vector B. So if I just wanted the length of the vector C, just the length of the projection of A onto B, that's the magnitude of A times the cosine of theta, or simplified into just being in terms of the vectors provided, it's the dot product of A and B divided by the magnitude of B. So if we then formally come to define these projections, we're going to have both a scalar projection and a vector projection. So scalar, meaning that our result is just a number. Vector projection, meaning that our result is a vector. We have that, we'll call the scalar projection the component of A in the direction of B, whereas the vector projection will just get the name the projection of A onto B. And it breaks down like this, the way I've written it out up at the top. So if the vector C from the diagram above is equal to the projection of A onto B, then that should be equal to the magnitude of that component, so the magnitude of C, times the unit vector in the direction of B, which is that piece that's multiplied in at the end. Since I already have the magnitude that I know I want, which is just that first part, and then I'm going to multiply that by the unit vector, which has the direction of B, but a magnitude of 1, meaning the magnitude is somewhat irrelevant in that unit vector. I'll call the projection the multiplication of those two pieces together. And again, the component of A in the direction of B is the part we just discussed above, where it's the magnitude of C, the length of that vector C. We can also rewrite this projection of A onto B so that we can clean up the notation just a little bit. And I'll stick with the same colors I had above. We'll still take A dotted with B. But I have two magnitudes of B hanging out in the denominator. So I can call that the magnitude of B squared. If I'm looking to just simplify the calculation. And then that value comes out to just a scalar. Since A dot B is a scalar value, the magnitude of B squared is also a scalar because they're just numbers. And so I'm going to multiply that into the vector B. So in the end, we can see that the vector projection actually does come out to a vector because it's just a number times the vector B. Also, a particular thing to note about this projection is that even though I'm projecting A onto B, I only have to use A in the calculation once, and every other vector in the calculation is B, the one that I'm trying to get onto. But while this new formula for the projection is certainly easier to work with mathematically, I think something is lost if we sort of don't look at those two factors independently. Or at least when I'm trying to remember the projection of A onto B, it's that top line that I remember, is that it's a magnitude times a unit vector in the direction of B. That always helps me remember it. Oh. But if we come back to that same diagram, but this time look at one more vector, which is now the vector D. If I connect the tips of vectors C and A together, that's going to be a component of A that is orthogonal to B, since I've drawn it along that orthogonal line that I constructed for myself. And we'll call D the orthogonal projection of A onto B. So it's just going to give us the part of A that's orthogonal to B, which means I could take my vector A and break it down into components that are both parallel to B and orthogonal to B. Which can oftentimes be helpful if I'm attempting to reduce a two-dimensional problem into two separate one-dimensional problems. So if I take just the vector addition of those two new vectors, C and D, the yellow and the magenta ones combined, that vector sum gets me all the way back to A, since I start at the origin and end up at the tip of A. So if I add C and D together, I get A, which means if I'm looking for a formula for that vector D, I can just take my original vector A and subtract C, which, remember, C is the projection of A onto B. So if I'm instead looking for the orthogonal projection of A onto B, instead of the standard projection of A onto B, I'll still start by finding the standard projection, but then I'll take A and subtract C. Which that'll probably make more sense if we put it into practice. So let's do that. So we'll take the vectors u and v as provided above, and we'll calculate both the projection of u onto v and the orthogonal projection of u onto v. So if we break these pieces down, u would be the same as vector A in the previous examples. V is going to be that vector B, since that's the one I want to project onto. So if I'm looking for that projection, which is u onto v, I should take the dot product of u and v, which should be 5, 3, dotted with 2, -1, divide that thing by the magnitude of v squared, which should come out to the square root of something squared, and where that something is each of those components squared and added together. So 2 squared plus -1 squared. And in the end, take the dot product, not quite the dot product anymore, because this is just a scalar value. So I'm just going to multiply that scalar value into the vector 2, -1. So upon doing that, let's see what we get. Across the top, 5 times 2 is 10, plus 3 times -1 will be -3. So 10 minus 3 is 7. Divided into that denominator, I'll have 4 plus 1, which is 5. I have the square root of that and then squared. So the denominator is just 5. And I'm going to multiply that into the vector 2, -1. Let's try that one more time. 2, -1. So if we're just looking at the magnitude of that vector that goes in the direction of b, that should have been 7 over the square root of 5, if we were interested in getting that, since we had our denominator squared, but the magnitude of the projection should have just been over the single magnitude of v, not the magnitude squared. So we can take one more step and just multiply this stuff together, which is a bit of an optional step, but I get 14 over 5 and -7 over 5. is the entire projection of u onto v. So then to calculate that orthogonal piece, I want, not a anymore, this is now the vector u, and I'm going to subtract the parallel part, or the projection of u onto v. So subtract that projection, the standard projection, it's in the direction of b, and it's of the vector u. So this thing should look like 5, 3 minus the vector 14 over 5, negative 7 over 5. Since in the end, that was our projection. And what do we get? 5 is the same as 25 over 5. So 25 minus 14 is 11 over 5, I hope. And then 3 would be the same as 15 over 5. And then we'll take 15 plus 7 to get to 22 over 5. Let's just look back at that math one more time. 25 minus 14 is 11. Yep. 15 minus negative 7 is 22. Cool. I like that math. And so there we have our orthogonal projection, which, to reiterate or to recolor, based on the above example, that orthogonal projection was the one that was in magenta. So one thing that should be noted about these projections is that they are not reversible. So for example, the projection of A onto B, which when we write the projection, we write the vector that we want to be going in the direction of as the subscript, and then the vector that we're actually projecting down below is the one that goes into the function or into the projection notation. It's rather important that this is not the same as the projection the other way. So it's not the same as the projection of B onto A. Since if we were to look at that projection, let's pick a color we haven't used yet. How about red? I don't think we've used red yet. If we look at the projection of B onto A in the diagram below, that would mean constructing an entirely different vector that goes in the direction of A. Something close to this, where if we again constructed some line that was perpendicular to A and look at where it intersected with B, we can see that that red vector is not remotely close to that yellow vector. They're not even in the same direction, much less do they even have the same magnitude. So the projections are not reversible to get the same result. We can take either projection, they just won't give us the same thing. And same with the components in each direction. So the component of A in the direction of B is also not necessarily equal to the component of B in the direction of A. So the dot product is something that's reversible, but the projection is not. Oh, and that's the end of this lesson.